In today's tutorial, we will discuss three special and interesting examples of nucleophilic substitution. First, this heterocyclic dichloride will react with methanol, which is both solvent and reagent. Then, this functionalized acyl chloride will react with an amino acid ester in a two-step process, one step and the second step, and finally in a one-step process this heterocycle will react sodium hydride as strong base applied. To learn best from these examples, please try first to solve the problems by yourself and afterwards listen to my explanations. So best would be if you now would stop the video. Okay, let us go on with the explanation. Methanol is the nucleophilic reagent with the free electron pairs of the oxygen as the nucleophilic center. Then we have this dichloride, and this is a secondary chloride, also this one sitting at a secondary carbon. We have a selectivity problem, but the oxygen has an important influence. Again, the free electron pairs can stabilize a positive charge in the alpha position. So an SN1 process will take place with the formation of a stabilized carbocation in the first step, mesomerically stabilized. And then this carbocation is trapped by the methanol with the oxygen as explained as nucleophilic center. Then we of course still have the hydrogen attached to the oxygen. Well, overall HCl is eliminated. And the final product is the one with the acetal as functional group. This chloride has been substituted by the methoxy group. Okay, also the last step is to some extent an equilibrium reaction. Is that all that is to say about this reaction? No, we should always keep in mind to think about stereochemistry. Both chlorides might be either in front of this whiteboard or behind the whiteboard. That means we have a mixture of diastereoisomers and enantioisomers. We should assume that we have a racemate here, it's racemic. Here we have a chiral center. This should be then also racemic, and finally we will get a racemate of this product, but the methoxy group will of course attack from the other side of that molecule compared to the chloride. So let us assume that we have a racemate, and in the drawing we just draw one enantiomer. We have marked that it is racemic, and this would mean the methoxy group should be on the other side of the molecule. So let's discuss the second example. We have the free electron pair as the nucleophilic, the nitrogen with the free electron pair as the nucleophilic center. The acyl chloride is the electrophile, despite having a second, a bit less electrophilic center here. The acyl chloride will react first. Addition-elimination process giving rise to a carboxylic amide the methoxybenzene, abbreviated as an aryl group. So, and well, HCl has been eliminated, therefore we need this tertiary amine as a weak base to trap the HCl. Otherwise, the amino group of this amino acid ester would be blocked by protonation, and not all of the substrate could get to the reaction, only half of it would react otherwise. So therefore, we need that additional base. In the second step, we need a somewhat more basic, somewhat stronger base. Sodium hydride is very well able to deprotonate the carboxylic acid amide. Then we have here the somewhat stabilized nucleophile, stabilized by mesomeric interaction with the carbonyl group, and in close proximity with bromide. An SN2 process will then make a ring closure reaction, although it is a four-membered ring as the product. It's well known that this reaction is feasible. It is a beta-lactame, a very important reaction, since beta-lactames are known as antibiotics. So let us go to the last example. Electrophilic center is here the alkyl halide and alkyl iodide. We don't have a profound nucleophile yet in this molecule. Well, for electrophilic substitution as an aromatic center, the OH group would activate ortho and para position. This nitrogen with its free electron pair will also activate ortho and para position. Overall, we have a slight delta minus here, but we can increase it by deprotonating that OH group here with a sodium hydride. Molecular hydrogen will develop, and with an increased nucleophilicity here, and it is sufficient to make an intramolecular reaction to substitute that iodide. The product that is formed then is this quinonoid system. The allyl group here is unaffected, and we will have formed a 3-membered ring here. And of course, sodium iodide. Also, these types of structures are interesting for synthesis of drugs. Thanks for listening. Bye.